the mic working?
Yes.
Okay, beautiful. Thank you very much for that introduction. So at any point, wave at me or say something if I don't immediately see your hand. I love questions, love to talk about what you're most interested in, not necessarily what I want to talk about. So I'm going to talk about 3 topics today. I thought I would start out first and just talk about my research, why I got into what I do, how that happened. Then an in-depth example of one of the things that I work on, which is explainable artificial intelligence, which has lots of connections into other things that I'm interested in and that I think are useful in today's thinking about AI. But also it is a more specific example of a kind of actual research that I'm doing. And finally, I'll have at the very end just some sort of thoughts about the peculiarities of computer science and how that may affect your work as librarians, which you can take or leave because I don't fully understand, of course, what you do. I do understand what we do in computer science, and I try to sort of project out. I may get it wrong, but we'll see. Okay, so what do I study and why and how do I do that? Well, one way of thinking about what I work on is, yes, I work in artificial intelligence. Specifically, I work in machine learning, this area of AI that's about how to improve performance over time from experience. And specifically, I do a lot of work in what's referred to as causal modeling, that is, trying not just to figure out associational relationships in the world. If I see this, I will also see this other thing. If I see these symptoms, I see this disease, okay? But causal inference, that is saying, if I change this thing in the world, this other thing will change. So we've all heard, correlation is not causation. There are ways actually to use complicated patterns of correlation to infer causation, and that's one of the things that we do in causal modeling. Now, another way of thinking about what I do is, if you think, okay, this guy knows something about causal modeling, well, one of the things we can do with that is better explanation. Because very often when people say they want an explanation, what they really want to know is kind of, what would have happened if things were different? That is a common kind of explanation and a very powerful one. And so when we started in the field realizing we needed to do explanation, I said, wait a minute, I've actually got a kind of secret weapon here, which is this idea of causal modeling. And then, what am I interested in doing with that explanation? One of the things I'm working on now is how to explain the operation of complicated computational systems. These are systems that computer scientists build, and one of the frightening things I'm going to tell you today is that computer scientists often, usually, don't really understand what our large-scale systems do, how they behave, and why. We actually need to analyze them to figure out what the heck they're doing. Yes, somebody wrote every line of code in that system, but we often assemble these systems from large pieces that other people have written, and then very often, even the pieces we've written have emergent behaviors that we don't understand. And so that's one of the things that I'm working on particularly now. So let me tell you about some kind of example projects sort of moving through my career history. So in the late 80s and early 90s, I was a graduate student. And one of the things that I worked on was screening for Alzheimer's disease. This is, how do you go out into the population and provide a very low-cost way of figuring out who might be at risk for Alzheimer's and who should go in and get a clinical assessment by a more expensive and more busy psychiatric diagnostician. So in my dissertation, I worked with some folks in the Washington University Medical School who had a bunch of data, and they were using fairly conventional statistical methods to analyze the data, and they wanted something better. Specifically, they wanted some kind of diagnostic rules that they could walk away with without having to have some kind of machine doing the estimation for them. Could they just walk out of the room after I was done talking to them and I'd run my neat machine learning algorithms, and could I tell them how to screen efficiently and quickly for Alzheimer's disease? And so I developed some methods for doing this, and then what these methods produced are very short rules that said if certain symptoms are present, it is much more likely that the individual has Alzheimer's disease. And I was just thrilled because these doctors were like, I can do something with that, okay? It is simple, it is easy to understand, and I can work with that. And so some of the themes that came out as I started the work say, of course, those models, those rules have to be accurate, but I came out understanding that also the explainability, the understandability of those rules was super important to this group of people, and justifiably so. I mean, they wanted to know how it worked. They wanted to know that it was what was going on kind of behind the scenes. So when I graduated with my PhD, I then went and did something pretty unusual, which is I spent 4 years working on Capitol Hill as a congressional staffer. I worked at what was at the time essentially a congressional think tank about science and technology called the Office of Technology Assessment. And we produced studies for the US Congress on science and technology issues. And one of the studies I worked on was, oddly enough, how to detect money laundering, how to analyze big data sets to detect when criminal organizations, particularly in the United States, are trying to launder money and thus maybe committing some kind of crime that means they don't want to reveal where that money came from. So if you look at a variety of crimes like drug trafficking, extortion, other sorts of crimes that are done by large criminal organizations, they generate lots of cash and then they need to do something with it. And the old thing that some of you may have heard, that I remember, follow the money. Yeah. Okay, this is what federal law enforcement does, is they go looking for these large transfers. And the idea was maybe we could detect this, particularly in wire transfers. These are bank-to-bank transfers. And so they came to the Office of Technology Assessment and said, we want you to study whether this could actually work. We ended up saying, no, it won't work. Because the patterns that indicate money laundering are so complicated that the current technology couldn't deal with it. So we put out a study after 18 months of studying this problem. We put out a report. The report talked about various things, and one of the interesting things, I went back to the report saying, let me just look and recall exactly what we said. One of the remarkable things in the report was that I actually brought up the question of explainability. And I said, one of the problems with some technologies, particularly neural networks, which were used at the time, that they couldn't explain their reasoning. They couldn't allow people to understand why a particular transaction might be flagged as suspicious. And I'll point out again, just like in the Alzheimer's case, this was a case of saying a human ought to look at this. Yeah. Not that this is an indication of real wrongdoing, but a human ought to look at this. And so one of the things we brought up is, well, if it doesn't explain, then it's unlikely to be trusted, and it's unlikely for also to kind of be auditable in terms of understanding what's going on, what might be, how the system might be biased. In the end, as I mentioned, we said really not likely to work, and ultimately Congress did not require the additional data collection that they were thinking about. And the themes here, accuracy, explainability, but also out of this came this idea of expressiveness. It was true at the time that the kinds of machine learning models, and I'll define that term in a minute, but the sorts of knowledge we were learning from machine learning was unable to express the complexity of patterns that were necessary to detect money laundering effectively. Because people, humans, very intelligent analysts were doing this by hand and with some really impressive graphical displays. And it was fascinating sitting down with them at the Treasury Department, and they would say, oh, this is somebody trying to evade taxes. This is somebody trying to shield assets from a divorce proceeding. Now we don't deal with that. This, however, this is money laundering. And I would be, okay, if you say so, that's really interesting. And then they would detail a very complicated pattern that shifted about every 6 months about what actually was indicative, in their opinion at least, of money laundering. So when I got back to a research environment, I said, wow, we've got this problem of expressivity. We don't have models that are expressive enough to deal with this sort of thing. And worked on this for many years. And then the National Association of Securities Dealers, which is the organization that the Securities and Exchange Commission at the time delegated responsibility to. They are a private nonprofit organization that does certification of stockbrokers in the United States. Everyone who sells securities to the public in the United States has to be a member of, then called the National Association of Securities Dealers, now called the Financial Industry Regulatory Authority, and you have to comply with their regulations. Now, the SEC does lots of other things, but this organization's mission is to detect, among other things, detect fraud. And they came to me and said, we heard you were developing these very interesting methods to look at very complicated patterns in financial transactions and detect fraud. Can you help us out? And I said, wow, you're really savvy about what I'm doing. Yes, I can help you there. And we did a bunch of work with them. To try to, again, screen transactions before they went to auditors who would actually go to the firms and look at much more detailed records. And again, we were able to do, depending on how you looked at it, either as well or better than human analysts at doing this initial screening, okay? By analyzing data and coming up with interesting patterns and then using those patterns to infer who might be committing fraud. Then I showed our models proudly to the folks at NASD, and I said, boy, we can do this great job. And they said, they looked at the models and said, oh, look, this causes fraud. And I said, no. And they said, oh, okay, fine. Oh, look, this causes fraud. And I said, no. and it was really hard to get them to stop doing that. And I said, okay, wait a minute, let's step back from this. Maybe this is what I should be doing. It's not what I'm doing right now, but maybe it's what I should be doing, because they clearly want this, and frankly, they should want this, because their goal was to prevent fraud from ever happening, not to detect it, not just to detect it once it happened. So they ultimately, after I talked to them for a while, said, absolutely, and what we would really like to know is what we can do to prevent fraud. And one of the analyses we did very late in the process was to analyze, because of some very fortunate sort of things that happened in the industry, we were able to analyze whether certain kinds of audits that they would go in and do actually prevented fraud, and found that they did. Okay, so there was strong evidence of a causal effect, which was really exciting and got me going, thinking, okay, a lot more people need this basic idea of causation. So accuracy, explainability, expressiveness, and causation now, really getting sort of further down the line to something much more interesting. Finally, as I mentioned, I'm very interested now in understanding how complex computational systems, including AI systems, work and don't work. And we've done various pieces of work, including one recently that I'll show you some examples from, where we find out that current deep learning methods, deep neural network methods, for doing certain kinds of problems often are profoundly brittle. That is, they work super well on exactly the task they've been trained on, and you move slightly off that task and they fall apart. And this is something that sort of anecdotally people in machine learning have known for a long time, and the degree to which these models, these statistical models, generalize and work in, when the situation changes slightly, vary. But in particular, many of the kinds of systems that are being built now have this brittleness to them. And it is one of the things that gets in the way of understanding what is actually happening in kind of the world of AI, because we as humans see systems that can perform certain tasks and we think, my gosh, if it can do that, it can do all these other things. If it can play chess well, oh my gosh, it must be super good at military strategy. No, turns out not the case. Lots of other things are required to do military strategy well, or business strategy, or whatever else you might want to think about. Okay, So, one of the things, the even more extent that I'm working on now is not just causation, but what is sometimes referred to in philosophy of science as mechanism. This is not just does X cause Y, but why does X cause Y? What's the process by which X leads to the effect Y? And understanding, particularly in complicated computational systems, what the mechanism is, how the thing actually works, is really important and difficult, challenging to come up with, but something that machine learning can at least help with. All right, let me quickly give some terminology, some of which I've already used. You may hear me and other people talk about a domain, and what we just mean is an area of application, say Alzheimer's diagnosis. Then when machine learning people say learning, they don't mean like what we do in classrooms, okay? They actually mean some algorithm, some computational process that can construct a model. Now, what's a model? A model is some formal representation in some kind of equation or neural network or tree structured thing, some sort of formal structure that I could write down or that I can store in a computer that represents something about the domain, something important about the domain, often relatively small amounts, but still represents something about that domain, and facilitates what I'll call inference here. And by inference, I mean a judgment or a prediction. So it could be a judgment just like, I see this symptom, I'm going to predict this disease. Or it could be, if you take this action, I can infer that this outcome will happen. Okay? So it could be all sorts of different things, but there's some sort of ability to use that model to make an inference and make an accurate inference. Machine learning is what I work on, but it's sort of part, as Bev said, part of AI in general. And what's interesting, and Bev has already mentioned this to you, is that machine learning is often used now as to learn what some people think of as kind of the heart of an artificial intelligence technology or an artificial intelligence system. And that's not just a machine learning person saying that. Many, many people are saying that machine learning has changed the landscape of what's possible to do with AI, because we can use what we've got, tons of data out there that this has radically changed in the last 20, 30 years. We have vast amounts of data about certain problems, not others, but about certain problems. And we've also gotten a lot better at how to do machine learning. Now, an example you may have heard of, but it's very scientifically down in the weeds for biologists, is there's a biological problem called protein folding, which is when you see a particular sequence, okay, in a protein, see a particular genetic sequence that produces a protein, then you know what the protein structure is, but you don't know how it folds. That is the configuration that protein will take on. And it turns out that the configuration of the protein is fundamentally important to how it operates in the human body. So for decades, there has been a protein folding challenge. That is this question of, if I give you a protein, tell me how it's going to fold. There's lots of tricks and things that people know how to do, and there's fundamental physics there that people know about, but none of that has yielded effective, accurate predictions of protein folding. And very recently, and now the top performing system is one that's based on machine learning, specifically based on these deep neural networks. And so AlphaFold 2, the second version of this, is up in the top. I think it may have been superseded recently by another system, but in any event, when it came out and competed in this world-class competition, people were stunned at how well it worked. It's also important to note, and I love this, they said the accuracy is not high enough on some of the predictions to really know that it's right, and it does not reveal the mechanism or the rules of protein folding. So we can't consider the protein folding problem solved. It works, but we don't know how, okay? And that's going to be a theme that you're going to hear a lot of from me and going forward. Also I want to point out that all of AI systems is not machine learning. Some of it's learning, but not machine learning. people who build these AI systems try them on a lot of different problems and learn over time how to better structure their system. And also it's just smart people who know the domain, know things about, say, protein folding, who structure the system in particular ways and set up the machine learning problems, and also who know about machine learning, so they set it up in a particular way that makes it work. And so when you hear, oh, the machine learning has figured out protein folding, no. Some super smart humans have figured out how to set up some machine learning problems that our current technology can solve. And that's great, super impressive, and it's led to state-of-the-art results. But it's not quite this sort of idea of, oh, you just dump the data in and you get this amazing system out. Just quickly, there are several different types of machine learning. The most common one that you hear about is what I will call associational learning, sometimes referred to as classification or regression. This is, I give you some set of variables and I want you to predict the value of some other variable or variables. And that is probably the most fundamental machine learning problem. An example would, of course, be to use patient symptoms to predict disease, say Alzheimer's disease. Then there's what I might call causal learning or causal modeling, which is given some context, we want to predict whether a particular action will produce a particular outcome, particularly whether it'll change the probability of that outcome. So if I drink more red wine, am I less likely to have heart attacks? Interesting question. Best answer is, I understand it right now, probably not. Okay, it used to be, we thought it did, but it's because it's super hard to make these predictions and make these inferences based on non-experimental data. Randomized experiments are fabulous, but it's hard to get vast numbers of people to either constantly consume red wine or not, and there's even some ethical issues we're concerned with. However, for instance, we used firm size and past behavior to infer whether an audit would cause a change in the probability of future fraud. And then there is something which machine learning people will refer to as reinforcement learning. This is taking a long sequence of actions, and then you get intermittent reward, and you want to then be able to learn how to act even more sensibly in the future so that you maximize your long-term reward. Okay, so it's a whole sequence of actions rather than just, I'll just take this one thing and see what happens. And reinforcement learning, for instance, is used for robot navigation or for game playing or for other things where you take these sequences of actions. Now, and an example is like a video game. Now, in the case of associational learning, you might think, this is like curve fitting, right? You kind of have a scatter plot, you sort of fit some curve to it. Yes, you're right, okay? That is the simplest sort of vision of what machine learning, at least associational machine learning is it's like curve fitting. And as this graphic shows wonderfully, this cartoon from XKCD, you can take the same data and you can fit lots of different curves to it. And so the question is, which is the right curve, okay? And that's not a simple answer. There's a very, very complicated set of answers to that, and this is the kind of thing that machine learning people spend a lot of time talking about and figuring out. Okay, so some of the research questions that motivate my particular work. There's a set of questions around what I might call model expressivity. Is a particular model class, a kind of model, sufficient to reason about causation, say, or to reason about the mechanism underlying something, let's say in a computational system or a biological system or an economic system? And as it turns out, many of the model forms that we have are the simplest ones that we can use to solve the particular problem we want to solve. And they're not rich enough in expressivity to represent this more complex stuff we may want to get to. And then how can we come up with those more complex models, and what do they look like and how do they work? There's also questions around learnability. Suppose I come up with a super complex model. Can I learn it from data? Can I learn uniquely the right model from data? Or are there a bunch of different models that are all equally consistent with the data I have that turn out to work very differently when I go to use them in some future context? this learnability question, or what's sometimes called identifiability, is a fundamental problem in causation, because you can, it turns out, find models, multiple models that are all consistent with the same observational data, but when you go and do experiments, they would make very different accuracy of predictions. And finally, I have a super big interest in applications. So great, I come up with all this stuff. What can I do with it? It's actually fun to do those things too, to use the tools and see what you can learn. Just quickly, what does it look like to do machine learning research? Well, some of what we do is theoretical. We actually prove theorems about things that certain estimators will converge over time if you give it enough data, that kind of stuff. Something that looks a lot like what a statistician would do, say. There's also algorithm design and system design that we just come up with. Here's how to design a system to do the things we want, and let's build it and actually put that thing together, put that thing into code. Then once we've built it, we run it through its paces. We try lots of experiments. We see how well it works. When I started in computer science, my uncle, who was an engineer, said, "Research about computers? What do we need to do research about computers for?" And I said, "Because we don't know how they work." And he's like, "Are you crazy?" And I said, really, we don't, because they're so big. They've gotten so big. We don't know how to do this. And when I teach research methods to our graduate students, I start out and I say, really, we need to do very careful research and have really careful research methods. And sometimes I get students looking at me like, "Come on, it's just all theory." And I say, "Tell me, how many of you, for every program you have ever written, it worked exactly like you expected?" And they all go, "Oh, well, okay, fine, yeah." And that's even if you write it correctly, okay? No bugs, you write it correctly, and then, oops, you just really didn't understand how it works. And this happens very frequently with even small programs and definitely with large ones. And lastly, once we do that kind of those experiments and analyses, we often come to fundamentally new understandings of what I might call the emergent behavior, of complicated sets of algorithms that end up behaving in ways we didn't expect, but we know why. We can come up with an explanation of exactly why that happens, even though it happens at a different level than the one that we wrote the code at. Okay. All right, now let me talk about explainable AI. So explainable AI is a class of techniques that enables users of AI systems to understand, appropriately trust, and effectively manage those systems. And I love this definition. This idea of appropriately trust doesn't say we want people to trust the systems, because they shouldn't trust some systems. Based on the explanations, we want to empower people to get the right level of trust in a particular system, given how they're going to use it. That's really the big concept here. So, in a super simple sort of graphic of how AI works, or how machine learning works, we've got some training data, we run it through some learning algorithm or process, we end up with some learned model or function, it's labeled here, and then that produces output when we put in some new data instance that wasn't in the training data, and then we use that output in some way, okay? And this comes from a lovely presentation from my DARPA program manager on the Explainable AI program. He was trying to explain to people who didn't know how machine learning worked, how it works. However, that all assumes that you're just going to use the output without any knowledge of how good it is or where it came from. And so right now, when we go through this process, there's a bunch of questions that arise. Like, should I trust this? What would happen if it really went bad? When does this model work particularly well? When does it work poorly, etc.? And these are entirely reasonable questions that only really started to come to the fore when people started using AI systems for critical decisions. And medical diagnosis, absolutely. Stock fraud detection, absolutely. These are important questions, But now that AI has taken on a much bigger kind of social role, these things are really important, and we realized we were really bad at them. And also, we realized that the current hot technology for machine learning, deep neural networks, were particularly bad at answering this set of questions. It was very hard to answer this set of questions for those technologies. So the idea of explainable AI, in theory, is that you've got this user at the other end now who says, I understand why you made that inference. I understand when I can trust you, etc. That's the goal, and I will tell you we are not there yet, despite years of research. And I'll tell you a little bit about, well, let me tell you first about why people are so fascinated by this, as they should be. So the number and importance of automated decisions has gone up, as I mentioned. The complexity of the decisions made by these systems has gone up. And finally, and I mentioned this, there is increasingly opaque models that are being used to make those decisions because they offer higher accuracy, but not higher explainability. Again, XKCD as a cartoon captured this exceedingly well. When this came out, I said, yes! So I hate to say it, but at some level you could think of deep learning systems as big piles of linear algebra, and unfortunately we do a lot of trial and error in machine learning. Well, that didn't work so well. Let's try it again with this other configuration. See what happens. Oh, that worked better. Great, we'll keep that. And we'll keep kind of evolving toward a better system, even though we're not entirely sure why moving in that direction makes the system work better. In some cases, we could post hoc figure that out, and in some cases, we have some engineering principles. But a lot of it has been trial and error because you can do what's referred to as cross-validation. That is, you hold out test sets systematically, and you see how well the machine learning system works when you apply the resulting model to the test set. So many of our most advanced and capable AI systems are based on deep neural networks, and unfortunately they are opaque. We do not understand, as Bev referred to, we don't know how they work. We don't know what's going on inside. I mean, we know how each individual computation works, but we don't understand the kind of emergent behavior of those systems. So let me give you an example. There was a much touted paper that came out about a decade ago applying deep neural networks to Atari. Okay, Atari games. Well, what's cool about Atari games is they're complicated, they're visual, and there's lots of actions you have to take to do well with them, and we know how well people do with them. And the researchers in this case were able to develop superhuman performance on Atari games with nothing except showing the screen, okay, encoding the pixels of the screen, and saying when the score went up. Okay, that reinforcement learning system used no other information except what was happening on the screen, and then it was choosing actions, up, down, right, left, fire, and there's one other button, I believe.
Question.
Yes?
So humans are limited by thumb speed on the controller. Did they limit the machine in any way?
They did not. As I recall, I should say. As I recall, they did not. However, there's been a lot of discussion about this because there's a successor system that plays StarCraft. If you're familiar with StarCraft, StarCraft is much more complicated, but there's this question of how much can the human see of the board versus what's being given to the AI system. Yeah, so lots of questions about that, quite legitimately, yes, so great question. So, superhuman performance, isn't that amazing? And what's also kind of amazing is that in my lab, we could redo the experiments, okay? We could run the same experiments and train the same system. We can't train ChatGPT, okay, in my lab, but we can definitely do this. And so we did, and we put out a paper that I'm gonna show you some results from. Okay, so one of the games is a Pac-Man-like game, for those of you who have played Pac-Man. It's called Amidar. And you control the little yellow guy. Okay, the yellow guy goes around and fills in portions of track, like eating dots in Pac-Man. And this is a trained agent playing Amidar. And it's doing really well. Okay, it's pretty cool. It like avoids enemies sometimes. It kind of stutters sometimes. It takes really cool turns. It takes risks. It does all this stuff, and people went, "Wow, it's doing so well." Okay, so really impressive behavior. Okay, problem. The knowledge, if you want to call it that, that's encoded in the model is super narrow. It knows how to play exactly this version of Amador. Only slight changes to the underlying task, and it kind of falls apart. And when we tell this to people in reinforcement learning, they go, "Oh, well, yeah, to change the task, sure." Let me show you what we did. What we did was we filled in one section of track. Up there, you can see it. It's the only change we made to the game. We made the game easier. Okay, you don't have to fill that in. Or you could do exactly the same thing you did before. And when we do this, the agent doesn't quite know what to do. It sort of stutters and goes over track that it's gone over before, and then it just stops and waits to die. Which is not good. Okay. Now this isn't like a specially chosen example. Okay, we did this over a vast number of different positions. And what I'm showing you here are the changes we made to the task. Sometimes we added a line segment, that is a piece of track you can go over. Sometimes we removed an enemy, should make the game easier. We shifted enemies sometimes and let them just start in different places. We filled in line segments like I just showed you. And sometimes we randomized where it started. In all of these cases, a human player would be whatever, and they would just go plowing on through the game. Instead, what you see on the right-hand graph between 0 and 1 shows you the percentage of score that it got when we made that change. So from something like 60% of the score all the way down to like 5% of the score. So huge performance changes for really small little changes in the game. Very brittle. Now, some of you may be saying, but what about ChatGPT?
Yeah.
Okay, ChatGPT isn't narrow. It seems like it can do anything. It's like super interesting. It's super general, right? Well, it appears to be general. To many people, many observers, ChatGPT and large language models, other large language models, appear to be very generally capable AI systems. I use the term appear very carefully here. There is actually very little evidence that these systems are showing artificial general intelligence. AGI is what we call it in AI. Not that we're getting there, but any particularly close to that at this point. But we do have a term for it because it's a goal. The first thing to realize is that large language models are trained essentially to do one thing, which is predict the next word. Based on tons of context, predict the next word. And in the stream of human-generated language, because that's what they're trained on. Most behavior of LLMs can be modeled by thinking about basically noisy retrieval of human-generated text and some accurate learning of syntax and what I might call simple semantic categories. So an apple and an orange are often interchangeable in a sentence. So even if it's never seen the sentence with orange in it, it might know, oh, okay, fine, no, listen to me. It might infer that they could put in the term orange when apple is the only one that it's seen. So there is a little bit of at least good evidence for some semantic generalization. But there's been a real problem doing research on these systems because with one exception, the large language models are not sort of open to exploration. They're not open sourced. And also, we do not, in many cases, know the exact way in which they're trained, nor can we deprive the large language model of certain training data to see what's going on. only researchers who are in the companies that are doing that work have that kind of access. And most people, including many computer scientists, are pretty ill-equipped to accurately judge the cognitive abilities of these language models. It's really easy to be fooled by this. And one way of thinking about that is beautifully summarized in this book from the 1990s, called the media equation. And the basic idea in the media equation is that people have this incredible tendency to treat computing machines, computing systems, as people and places. Real people and real places. And there's just wonderful social science research about this, where you take a social science finding about how people want to be kind to other folks and not tell them that they're messing up. And then you substitute a computer in. Like, you have a computer that has a really bad spell checker, okay? And if that computer asks the user, how did I do? How's my spell checker? The user says, pretty good. And then you go over to another computer, the user goes over to another computer, and that computer says, how is that other computer's spell checker? And the person says, actually, not so good. Okay, wild stuff like this. So realize people are super inclined to treat computing systems as people. And fascinatingly, they will deny it if you tell them that this is what they're doing, even though they've just done it and there's really strong evidence that they did. So you put large language models in front of people and guess what they're going to say? Wow, it's conscious, It's like a person. It is so good. And so we should all just kind of realize that there is a strong bias toward that most people have. I would highly recommend this article to you if you're, and by the way, the slides, I will happily provide the slides. ChatGPT is a blurry JPEG of the web. For a popular press article on large language models, it gives you a really good mental model to use to think about how these actually work. And I know that I am now, I got time? Okay. So let me just give you a little bit of technical detail on how explainable AI might work. Again, these are some slides from the DARPA program because they just beautifully summarize what's going on. So we've got a bunch of learning technologies. And the question is, how can we make them more explainable given where the current technology is? So one way of doing that is to basically augment these deep models with the ability to generate explanations. Let's get these models to explain themselves. If they can put out really interesting text, let's get them to put out text that's explanatory. And believe it or not, there's been work on this where people work to have a system not just put out this image that I'm looking at is a bird, but why the system thinks it's a bird. Now the problem with this is that it might produce a really convincing explanation that has little or nothing to do with how the system actually works. Okay, so there's a sort of fabrication problem here that could be an issue. There's some ways of dealing with that, but anyway, it's an issue. So you could have the system, have these deep neural networks learn how to generate explanations. Another approach is to learn models that themselves are interpretable. You can just look at them and kind of know what they're doing. There are classes of older models that are almost as good, or in some cases definitely as good, as deep neural networks that are much more understandable just by examining them. Okay, so some of the really good work on what is called learning a kind of model that's referred to as a probabilistic program that actually, and this is one on understanding how written characters are actually generated. And it's a model of the generation process so that it is understandable how that written character is generated. And thus, when you look at a particular written character and it says, I think that's a 7, it can actually do some description and it's just inherent in the model that it describes how that process happened. And finally, you can take a model that's an opaque model and learn a model of that. Learn how it works. Okay, so it's a model of a model. Which, yes, it makes your brain hurt. It really made my brain hurt because guess what? This is what we chose to do. This is an early version of it, of some work in this sort of approach. But we chose to take that approach. We worked with Charles River Analytics, which is a company in Boston, and we came up with systems that would look at a model that, say, plays Amidar, okay, and then give you this nice interface that describes what the model thinks about why the agent is doing particular things. And this is referred to as counterfactual explanation. That is, we said, what if the world had been a little different? How would that agent have acted? Okay, and that's a way of figuring out what's important to the decisions that the agent is making. And so this is the approach. This is drawn from a paper that Charles River wrote later. And one of the things they show is that people trust these results more. Okay, they're happier with those results. Not necessarily, that's not a really strong indication that the explanations are accurate, merely that people are happy with them. However, we also found out this brittleness, this really strong brittleness, that typically these causal explanations that we were generating were only accurate for very specific contexts. And so each one was correct, but you give a person 10 of these and they can't do anything with understanding how the system is going to act in other contexts. One of the reasons you want to explain things is you want people to take away in the end an understanding of how the system operates and then allow them to kind of generalize about future behavior. But all we could do is tell them in this very specific instance what might be important, and you just moved a little bit off to one side, and who knows what would change the system's decisions or actions. And this, in turn, led to two new areas of research that we have been pursuing since then. One is this question of competence awareness. If we can't act competently, at least we can know where we're incompetent. Okay, so it turns out that we can understand, again, this is some work we did with Charles River and the University of Texas, where we were doing robot navigation and trying to make the robot so it could say, whoa, can't do that. All right, not gonna act competently in that space over there. Don't send me there or else I'm gonna crash, okay? Or I don't do this at night. Just send me there during the day and I'll be fine. So you could wait and choose to do things differently. And then there was a program we just concluded, research, again funded by DARPA, about what's called adapting to open world novelty. This is if the world changes, maybe we're not competent, but we can adapt quickly to that new environment. And one of the things we did, and what I'm showing here, video games once again, is Angry Birds. Where Angry Birds, the game changes kind of consistently over time. They add in new birds and they add in new structures and they do other things. And the question was, could we adapt super quickly to those new contexts? And we did, largely by having a really deep mechanistic model of how that environment works. So, finishing up here, one thing I just want to make really clear is that we are really early in both deep learning and explainable AI. I would say deep learning is pretty much now at the peak of inflated expectations. And explainable AI, we are still way down, okay, right after the technology trigger. We've been, we know we have to do this, but we're just not very far along in doing that. We as a field, okay. Finally, last two slides on some thoughts. So, first thing is computer science is weird in some ways. You may not already know this, but computer science, the top publications, the archival publications, are conference proceedings, not journals, which causes lots of distortions. Okay, we constantly have to explain this to people up the chain of the university administration, and it causes some serious problems with indexing because a lot of times computer science conference proceedings are not indexed in the same way that journals are indexed. And when people do cross-field comparisons, computer science is always really wonky because they're looking only at journals usually, and they should be looking at conference proceedings. There's also, like there is in many journals, or there used to be in many journals, a cliff. If you go back in time, you hit this time that is not digitized anymore. But what's really frustrating is journals have had a profit motive to digitize all of their archive. And conference proceedings, there's no publisher there or rarely were there publishers, and sometimes it's split across multiple publishers. So there's some conferences that have digitized the entire thing, and some which haven't. So it's a weird kind of literature situation. Also in computer science, one of the super important things is not just literature and data, but code. Code is an archival thing that unfortunately is an expiring asset, okay? Code, the day it is written, starts to decay. And after a few years, you start losing compatibility with libraries. And then you start losing compatibility with hardware. And then you start losing compatibility with programming languages. Either the programming languages evolve or they just go away. And so that's a really long-term issue, but the much more near-term issue is what I would call library problems, not the sort of libraries you're thinking of, but software libraries that just get updated and they no longer are compatible with the software that we've written. And that is like, if you go back 100 years, you can reproduce somebody's physics or biology experiment. It is really hard often to reproduce somebody's computer science experiment. Final thing I'd point to is that large-scale commercial R&D is happening because of the incredible relevance of computer science in general, and AI particularly, and machine learning particularly. And so we are having major results come out from Google, Microsoft, Amazon, other large tech companies, and it's almost inaccessible, okay, in the sense that we don't have the resources, we in academia don't have the resources to reproduce that experiment. We don't have the data to reproduce that experiment. ChatGPT, the model underlying it, GPT-4, my understanding is that it was about $5 million to train. Okay. I don't have those kind of resources in my lab to spend that much on the computing necessary to train a model like that. So this question of how we deal with that and how we can test the results coming out of those kinds of commercial research endeavors is a really interesting question. I don't have a good answer for you. It is an issue. Last slide. I was given a beautiful list, okay, thank you so much, of things that might be that librarians could possibly do for us. And I said, I know what I'll do. I'll do green check marks and red X's. And I was like, green check, green check. So I decided to order it, okay? So this is my rank ordering, just so you know, of like what seemed most useful to me. You might get an entirely different answer from someone else, but anyway. That'll be available in the slides. And that's my email address if you have questions afterwards.
Okay, we've got maybe 25 minutes for questions.
Excellent.
Can I bring you this mic?
Sure.
You don't have to stand with us.
I have to ask, is DARPA, and you have an inside track, are they talking to Google and these large tech companies to sort of work together on
To
this?
some extent. There's also a lot of discussion and effort at NSF and DARPA to provide large-scale computing resources to researchers. We'll see where that goes.
Okay.
Also, I will point out that we at the Information Computer Science College of Information Computer Sciences here, have got major support from the state. Okay, millions of dollars from the state to have large-scale computing resources to keep our research active. Okay, and so the Massachusetts Green High Performance Computing Center, say that 10 times too fast. The MGHPCC, which is located in Holyoke, was put together by a consortium of universities in order to house large clusters. And so that was MIT, Harvard, BU, Northeastern, and UMass. I believe I've gotten that right. And UMass was a leader in that. And we have put several major clusters there of machines so that we can do the research that we need to do, and our graduate students have access to that. And so it's huge, it's an enormous resource, but it was, it would have been a major hindrance to our ability to compete essentially in the international marketplace of ideas if we didn't have that.
Let me just add that the UMass Computer Science Department is one of the top 20 in the country. So it's doing very well. In terms of that's including research funding from National Science Foundation and DARPA.
So at Colby, last year we started an AI institute, and which I'm affiliated with. But as part of that, we brought Dr. Friedler, who was one of the people that wrote the AI build blueprint, right?
Excellent.
And I was sort of interested. I tried to get a little bit more of a robust conversation with her about it, but so I was sort of interested to see what you think about something like that. So
for those of you who don't know about this is the blueprint for an AI Bill of Rights. The name was very carefully chosen because it's not an AI Bill of Rights, and by the way, it's not Bill of Rights for AI, it's Bill of Rights for us, about AI, just to be clear. But instead it's not a Bill of Rights, it's a blueprint for a Bill of Rights. It is a fantastic, I feel like, sort of fusion of all the things we should be thinking about in terms of how to make AI technologies particularly compatible with the way that we believe our country should run. But what is challenging, and everyone will say this, is what to do next. That you can state these principles, not that was easy. It was incredibly hard, as I understand it, to put that together and get buy-in and agreement. But it's going to be even more challenging to now say, what do we do next? And one of the challenges is that when I say AI, I might as well be saying technology. It is this massive, massive area. And things that were invented 50 and 100 years ago can be called AI. Linear regression is AI, okay? Simple statistical methods can be thought of as AI. There's a smooth continuum. And so I think we're going to have much more fine-grained categories to think about what to do in a public policy context.
Because they called it just automated systems. They never actually, that's how they ended up defining it, which I thought was really interesting. And my class in the fall will be about AI in society, and I'm going to use it. I'm going to use the idea of contested, right? Like contested knowledge, but I'm going to now add your little thing onto that, because I'm like, I really like some way about thinking about the system. Yeah, it was really good. Yeah, it was awesome. Yeah.
So I have a question. When you started talking about like the protein folding abilities and these models, and I can tell you that 15 years ago as an undergraduate bio student, we would sign up to let our computers, when they were otherwise idle, do brute force modeling of protein folding. Like, have we improved from that? Like, I understand that we have more computing capacity now, but like,
let me just, that's a great point and a super good question. Realize that many of the capabilities that have improved over time, it's just Moore's law. Okay, it's just the chips get faster. Okay, and boy, computer science is just milk that for everything it's worth. It's so cool, the stuff that we can do now that we couldn't do before, just because chips have gotten faster. But yes, we are way beyond folded. I think it was what.
And it was like out of one of the national science institutes, and like you signed up to volunteer your computing power to.
And my understanding is,
So folded is actually a game for protein folding.
You're right.
Humans interact.
That's a good point.
And
Yes.
I
Was it
wanted
folding
to
at
build
home?
on it.
Yeah, it was something like that. But it was like, yeah.
I wanted to ask
Hold that
whether
ball.
humans have made proteins that have then been verified that the AI has not been able to do.
Well, I don't know.
Okay.
That's a really good question. There is this interesting kind of question of there's a set of proteins we know about right now, and we know how large numbers of them fold, but it may be that the world, it's the novelty sort of thing that I've talked about. It may be that the proteins we create in the future artificially may work very differently than the ones that we do now. And it is not clear that what kind of knowledge is being learned by these systems, and whether that will generalize or whether it will be one of these cliff situations. I will point out that deep neural networks are what in the trade we call universal function approximators. That is, give it any set of inputs, and with enough layers, it can replicate any set of outputs if you give it enough training data. And so that's amazing. This is like this holy grail. It's a universal function approximator. But what it means is that if I take a point right here and I see what happens to the output, if I take that point and slightly change it, I have no idea whether the output is going to totally change or just change slightly. I may think it's a small change, but the network may not. And so the universal function approximator is like a double-edged sword, is that if the population of data changes a little bit, it may not work well. And that's what we showed certainly in the Amidar case.
So I have a much more casual layperson question. I asked kind of something similar earlier this afternoon, but that's like in your current fields, like when there are all of these conversations around computer science and AI, like there's a new season of Black Mirror, like how do you feel about like lay people processing that stuff? Are you excited that there's more dialogue about it? Does it annoy and frustrate you that people misinterpret like your life's work?
Yes. Okay. Yes. All of those
Is Black
things.
Mirror
I
actually
feel-
spooky to you, or is it getting it wrong?
I haven't yet seen the new season of Black Mirror, so unfortunately I cannot
I mean, I haven't either.
comment.
But.
Oh, okay. I mean, I have to admit I had a little bit of a freak out last night when I saw that the headline in the Washington Post was Chuck Schumer, says AI regulation is coming or something. That was the top story on the Washington Post, what used to be my hometown newspaper. And I never thought I'd get to this moment. This is just so weird. So on the one hand, it is fabulous and wonderful. And on the other hand, it's very frustrating when I see people, this is why I talk about the media equation, because I read that book in graduate school and I said, wow, or shortly after graduate school, I guess. This is so perfect. And it does describe this moment we're having, where people say, again, if AI can do X, then that means it can do Y. Because if a person can do X, they can also do Y. But that's not how AI technologies work. And also just, by the way, if you really want to do me a wonderful favor, you can all use the term AI technologies, not AI.
Yeah.
AI is a field, but it is not a thing, okay? We don't have artificial intelligence. We're not going to have artificial intelligence for a long time. So if you say AI technologies, it kind of softens a little bit and says, oh, these are technologies trying to be AI. And so I get really disturbed when people talk about AIs are doing X, Y, Z kind of thing. That's something where I kind of get highs. But so it's wonderful and terrible all at the same time. And we're, as a field, we are learning, I mentioned this to someone else, that we're sort of having our the moment that physicists had in the 1940s of saying, oh hell, we are no longer kind of academic backwater working on our own little stuff. This is huge societal impact. And I've always had an interest in public policy and social impacts of technology, but wow, has it become important recently because of all the stuff that's happening.
I just want to add one thing, which is First of all, to answer your question, I think it's marvelous that people are getting engaged, even if Chuck Schumer doesn't with sleep. But the point you gotta realize is that as soon as something really works, like Siri and Alexa really work, it's not AI. People say, oh yeah, that's just, what we expect. So as soon as we achieve a little bit, it goes into the background, and everyone assumes that's what computers can do, and they take it for granted. I mean, Siri will never go away, Alexa will never go away. But this is a natural language programming assignment, for how many graduate students got the PhD to invent those things? 30 years ago, 20 years ago. And now you take it for granted.
But Bevel, remember, Victor Lesser, who was a major senior mentor of mine, spent his entire early career working on speech understanding. Okay.
30 years.
He came up with one of the first systems for speech understanding. He and a bunch of other people, called Hearsay 2. And this was enormous amount of work. And he is now, long time emeritus faculty, okay? Long time ago. And we finally have speech recognition. It's totally amazing.
Yeah.
But that's how long it took. And just what Bev said, everybody goes, oh, that's
Yes, nothing.
Optical character recognition used to be AI. Google search used to be AI. These things that we just sort of laugh at now and say, well, keyword searching used to be AI. Not AI anymore.
But it's progressing much more quickly now. So you have to recognize what took 20 or 30 years for Victor Lesser to do. It's happening in 3 or 5 years now.
Yeah.
So what are we gonna do with that? And what is the social implication of all this?
Where do you come down on saying thank you to Siri?
Please don't.
On the other
Siri is not human. Do not treat it as human.
but you may thank computer scientists. But all the other
So in my limited, coming to this without a lot of background in it, I see a lot of potential for misuse. And I don't bring any of this up in a judgmental way whatsoever, but I'm curious, from your perspectives as the experts in this field, what do you think are the biggest potential ethical concerns or things that we should be paying close attention to? Obviously, this has incredible applications that could change life for the better.
Mhm.
I think we can all also see that there's potential for misuse or data breaching or that kind of thing. Knowing what you do, that is so much more than what we know, what do you think are the bigger risks or?
Great
She's
question.
asked a better question than I was going to ask, but my question was going to be about recidivism in the judicial system. We've got judges who know nothing about the algorithms, using it and impacting real humans, but your question was much better. But that's my example that I was going to ask about.
So I had an example of that. If you have a database that says black people have recidivism at a higher rate than white people, it's because usually the database has only people who represent who are in the jails now. And that is high percentage of black people, let's say, or minority people.
And sometimes it can also represent previous bias in the human decisions.
And so
And sometimes,
the databases have to be cleaned up. This is not accurate.
and really there's been some very good work recently on how to audit any machine learning model or any